Starting at figure 1, we look at cell A and cell B. An event happens when neurotransmitters are released from the terminal buttons in cell A. Four things can occur. They can scatter and float, they can go back into the terminal button, they can be deactivated for being in the interstitial fluid for too long, or they can bind to the binding site of the dendrites on cell B. Now focusing on cell B, the neurotransmitters bind to the ion channels on the lipid bilayer, causing the channel to open as seen in figure 2 here. Once these neurotransmitters bind here, these ion channels will open. When it opens, it allows sodium to come into the cell, and sodium comes into the cell by two forces, osmosis and electrostatic pressure, and it brings the sodium down this concentration gradient. And since sodium has a positive charge, but the inside of the cell has a negative charge, then opposites will attract. And to measure these charges, we use an oscilloscope. If the neurotransmitter binds to the binding site, causing the channel to open, there will be a rise seen on the oscilloscope as seen here. That rise is called an EPSP, and it shows a depolarization. Before that rise occurs, the cell is at rest, which is going to be at a negative 70 millivolts. EPSP occurs when ion channels are open on the dendrites. After that, when we start to see multiple neurotransmitters binding to the binding site, threshold of excitation occurs when multiple neurotransmitters bind to cell B's. And multiple EPSPs are known as the process of temporal or spatial summation. This increase initiates an action potential. Action potential is reached when the millivolts is reached to a negative 65 here. And all of this is occurring while sodium is coming into the cell. It's also, all of this is being generated at the axon hillock. And while the sodium is coming into the cell on the oscilloscope will reach a negative 55 from a negative 65, which is hyperdepolarization. At this point, coming down into hyperdepolarization and then going back up, the cell is going to reach equilibrium, which is going to cause it to go back to a negative 70, which is going to be, the cell is going to be at rest. Then potassium gates are going to open. Potassium gates are going to open, and the cell is now going to become positive. And then the cell, as potassium gates open, the ions they repel against each other, and it causes potassium to leave the cell. Action potential propagates along the axon from the axon hillock, which is saltatory conduction. At each node there is a potassium gated channel and a sodium gated channel, allowing the sodium to come in. And let's just picture one of these here also. It allows the sodium to come in, and when the sodium is coming in and the sodium and potassium repel against each other, potassium is going to leave the cell. The EPSP occurs along the nodes of Ranvier, and once, let's say like this is going to be time 1, and this is going to be time 2 and time 3. At time 1, the cell is going to be at rest. Once this cell reaches action potential, this cell is going to start to cause a rise. Once this cell goes back to rest, this time number 2 here is going to reach action potential, and time number 3 is going to cause a rise. And once this one is at rest, this is going to reach action potential, and it's going to come down and be at rest. And once it's back at rest, and the action potential reaches the terminal buttons, it interacts with calcium, and vesicles then bind to the presynaptic membrane as seen here. And due to excitosis, the vesicles slowly open, and molecules of neurotransmitters are released into the synapse, released into the presynaptic membrane here, and then they're released into synapse and binding to the postsynaptic membrane, and it's just starting the process all over again. And that's my neuron story.